Hi everyone. Today I'll be walking you through the tree farm problem, and yeah, let's get started with part A. So part A asks us to fill out this function tree mismatches, which takes as input two trees, T1 and T2, that have the same structure, and it asks us to iterate through those two trees and compare corresponding nodes, and if the nodes don't have the same value, return them as a tuple. So first, let's take a look at these doc tests here. I just sketched out what trees they created. Essentially, you call the function, you assign it to some variable a, and then calling next on a repeatedly will yield all the tuples. So this tells us that tree mismatches is actually a generator function because it's yielding an iterator that will basically iterate through every single mismatched tuple. And that's a key part of understanding. That's the key thing you need to understand in order to solve the problem. So as you can see in my diagram on the left, or sorry, on the right here, we start at the top and we compare the two root nodes, 1 and 2, and they don't have the same values, so they're yielded. And that's how we get this first output. Similarly, then you go and compare 3 and 4, and then they're not the same, so you get this output. And you do the same for 5 and 6, and you keep going. Just note that the corresponding nodes with 7s are skipped because they actually have the same value, and so they're not mismatched, and so you don't yield them. Great. So how would we go about solving this? Well, first things first, it's a tree problem, so you're going to need to use recursion to traverse the tree, and it's a generator problem, so it can get a little weird, but let's just start with the base case. So if you're at the root node, you essentially just want to compare your value with the other tree's value. So let's just say if the values don't match up, use a different color here. If the values don't match up, so if T1 dot value is not equal to T2 dot value, values don't match up, then you want to yield them as a tuple. So you're going to yield T1 dot value, comma T2 dot value. So the reason we do this is, well, let's say we just have, just two roots. You're just going to compare them and then yield that. So that's what you're always doing. It's sort of like a base case. So then next up, we have a variable n that is assigned to a blank. And we don't really know what to fill in there, so let's just move on and look at the for loop right after. And the for loop says for I in range n. So that tells us that n needs to somehow represent, I guess, like it's like the number of things we're going to be iterating over. In this case, we're going to be iterating over branches, so we can conclude that n is the number of branches, which we can write out by just saying length of, you can say T1 dot branches or T2 dot branches because the trees have the same structure. So I'll just write T1 dot branches, but just know that you can do either. Great, so now we're on to the for loop. And the for loop says for I in range n. So we're cycling through the branches now. And here's where the recursion comes in. So we see we have this variable branch mismatches set to something blank, and then we have a for loop. So first, let's think about what a recursive call in a generator function means. So calling a generator function will give you back an iterator. So let's just say I called this function on a smaller subtree. That'll give me an iterator that returns all the mismatched nodes in that smaller subtree. So here branch mismatches, which we can just assume means like, just assume represents a recursive call, that's going to be an iterator. So let's just try filling out a recursive call here and see where that takes us. So tree mismatch is called on what? Well, we want to call this on corresponding branches in both the trees. And we notice that we're in a for loop that cycles between, that cycles through all the branches. So we can actually just say T1 dot branches at I, right? We want to compare the ith branch of T1 to the ith branch of T2. So we take T2 dot branches at I. So this will yield, so this will store an iterator that goes through basically the subtree T1 dot branches I and compares it to the subtree T2 dot branches I. And yeah, and will return all the mismatched tuples. So for our final 4 here, we can actually, just to get the rest of the mismatched things, assuming that I've already done the comparison at my node, the rest of the mismatched tuples will just be all of the things contained in branch mismatches. So we can just say for val in branch mismatches, so for every value in branch mismatches, just return that value, or I guess yield that value because we're in a generator function. And that'll get you the rest of the mismatched tuples. Great. Thank you for listening. All right, hello everyone. So now we're gonna do part B. So let's get started. Okay, so part B asks us to fill out this method called the tree generator 2000. And it accepts an integer n, and essentially it's a generator function that every time you call next on it, it'll yield a larger tree. And that larger tree will fulfill a few specific conditions that are outlined right here. So let's talk about these conditions real quick. So first, every non-leaf node needs to have n branches. And the value stored at each node is equal to the number of nodes beneath it, and the depth of the tree is going to increase by 1 every time next is called, and that's how you get larger and larger trees. So let's look at this example. It's very helpful. All right, so consider the case when n equals 2. So consider the case when n equals 2. So in this case, each of these trees represents a different spot on the iterator. So number 1 here is the first time the iterator is called. Number 2 is the second time. Number 3 is the third time. So the first time, you're just going to yield a tree with 0 as its value. And it's just going to have one node, and that's the root. The second time, you're basically going to create a new, so you're going to have a new root. So this is your new root. And it's going to have n branches that fulfills the criteria. And the value of the new root is the number of nodes beneath it. 2, so that works out. Similarly, 6 is our new root here for the third time the iterator is called. And that is because, well, first of all, it has 2 branches beneath it because n is 2, that is correct. And also it has 6 nodes beneath it. So this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Great. So how would we go about implementing this? So as you can see, they actually give us one method here that we could use, or we should use when writing our solution, and that's tree copy. Basically, you pass it, you give it a tree, and it'll give you back a copy of that tree. Okay. So how do we go about solving this? Well, first things first, the key is really in like looking at the diagram they gave us. So first time you call next, you're always going to get just a root, no branches, and it has a value of 0. And that's also true from the doc tests here. So maybe it's a good idea to initialize this tree variable, which looks like the thing we're going to yield. Why don't we just like initialize it to tree 0, which is exactly what this is right here. So that seems like a good place to start. Now, this iterator actually is going to be infinite. Like you can call next on it as many times as you want, and you'll keep getting larger and larger trees that fit the criteria mentioned in the problem. So maybe this while loop here should have a condition that will make it such that the loop loops forever. And so if you just say while true, that will actually do that. So while true, true is always true. It's just going to keep looping. Now, recall that the first thing we're going to yield is, once again, this number one case here. And so we initialize tree to that. And so I guess the first thing we should do is just yield tree. Because, we're in the while loop. First thing you want to do is just yield it. That is your first thing. Now, we need to construct the next case when you call next for the second time. So here's how we'd go about doing that. To start, we can look back at the diagram and try to pattern match. So as you can see, the variable we're filling out next here is new branches, and that's equal to something. Now, new branches is probably going to be equal to the branches of the next iterations, right? So new branches here is actually just going to equal it's going to equal this here. Or new branches for the third case is actually just going to equal these two things. So the branches of a tree are actually just a list of trees. That's how it's defined. And so what we can say is this definitely has to be a list. We can actually just put an opening bracket here because we know it's going to be a list. So let's go back and see if we can pattern match. And you'll see that the number of trees, the number of branches the next iteration is going to have is whatever value n is. So in this case, n is 2. So you're adding on 2 branches here. And similarly, you're adding 2 more branches to the third case as well. And so what we can just say, and one more thing to notice, is that the branches that are being added are actually the tree, the entire tree from the previous iteration. So this here, so let me just use a different color. This was our original tree from the original iteration. When we call it again, we're just going to put 2 copies of those, and those are going to be the new branches for our next iteration. Similarly, we're going to look at this entire tree next, and for the next iteration, that entire tree is going to be the branch, quote unquote, or the branches, quote unquote, for the third iteration. So noticing that, we can actually just make the branches a copy of whatever tree we have right now, which is, you can think of like the previous iteration. And we're just going to add on n of those. So that's like saying for I in range n. Cool. Now, we have one more blank to fill in, and that is basically going to represent the new tree that we're going to be yielding. Because if you look here, we're at the end of the while loop. And so it's going to loop back to the top and yield whatever we have here, yield tree. So tree needs to equal a new tree that's going to have some new value and then new branches as its branches, because that's what we defined earlier. So its branches are going to be new branches. And its value is not known to us yet, and we're going to figure that out by pattern matching again. So we're going to scroll up, and we're going to see that the value at the top, at the root node, is actually just, and according to our criteria, it's the number of nodes below it. So in like the number 2 case, you can see that there are 2 nodes below the root, so the value of the root is 2. In the number 3 case, you notice that there are, well, 2 nodes directly below it, plus the value, basically, you can think, because the value of each of these nodes represents the number of nodes below that node. And so it's like plus the value of that node times the number of branches. So to summarize, the way we get 6 is by saying, look here. So we have the 2 nodes directly below it, plus the number of nodes beneath those nodes. And we know that number of nodes beneath those nodes is just the value in those nodes. So it's just 2 in this case. So it's 2. And then that times the number of branches there are. So that's 2. And that gives us 6. Or to generalize this formula, since n is 2, it's actually just so it's n plus n times the value of the tree. So that is our new value. And that is all. Thank you for listening.